Okay, in the last video we learned what transverse and longitudinal waves are. This video is about the properties of waves. We're going to start with a transverse wave. And just to recap from the last video, transverse waves, they oscillate perpendicular. So these particles or the wave are oscillating up and down. You need to know what an amplitude is. An amplitude is from the middle to the peak. So that's amplitude. Or from the middle to the trough. That is also amplitude. Wavelength is from peak to peak or trough to trough. So if I extend this wave a bit further, from peak to peak, that is the wavelength. And I can extend the wave backwards that way as well. And wavelength from trough to trough. Common mistakes people make is they think amplitudes from bottom to top or from top to bottom, but it's not. Amplitudes from the middle to the peak or middle to the bottom, middle to the trough. One complete oscillation is from where the particle starts and completes a whole cycle. So if the particle's starting here at point A, it's oscillating up, down and back to where it started. So A to B is one oscillation. A to B is one oscillation. You also need to know what frequency means, and frequency means how many waves per second. Frequency is number of waves per second, and that's measured in hertz. Capital H, little z. Frequency is number of waves per second. So for example, if we had 50 waves in 10 seconds, that equals 50 divided by 10, which equals 5 hertz. You also need to know what period is, but we'll talk about period in a minute. And for longitudinal waves, we need to know the same detail. Longitudinal waves. Wavelength is from period of compression to period of compression, area of compression to area of compression. So from that area of compression to that area of compression is the wavelength. Amplitude is how much the particles oscillate, so that small area there is the wavelength. Sorry, not wavelength, amplitude. And we also have the areas of rarefaction, areas of compression. Again, you need to know frequency, and that's the number of waves per second. So the number of waves per second divided by the time gives you your frequency. And you also need to know how long each oscillation takes, and that's called the period. Period is how long equals how long one oscillation is. How long one oscillation takes. And as it's measured in time, it's measured in seconds. And there's an equation given to you on the equation sheet that you need to be able to use. Period equals 1 divided by frequency. So if we go back to our example earlier, where we've got a frequency of 5 hertz, the period for that would be 1 divided by 5. Don't take any risks, use a calculator. 1 divided by 5 equals 1.5. Press the SD button, equals 0.2. So each of one of those waves from our previous example would take 0.2 seconds. And there's another wave equation that's very, very commonly used, and that links wave speed, frequency, and wavelength. So wave speed, and that's measured in meters per second, just like in forces. Wave speed equals frequency. That's measured in hertz, which we've just discussed, times wavelength. and it's a length, so it's measured in meters. And the wavelength we could get from a picture, from a longitudinal wave, or we could get from a picture of a transverse wave. It doesn't matter as long as we get these numbers. All of them could be simply given in a table or a picture. Wave speed equals frequency times wavelength. It is very common that you get given the wave speed of 3 times 10 to the 8 because that's the speed of waves in the electromagnetic spectrum. So we had a wave speed of 3 times 10 to the 8 and a frequency of 5 Hertz, and we want to know what the wavelength is. We substitute the numbers in, then we rearrange. So the opposite of times 5 is divided by 5, so we get 3 times 10 to the 8 divided by 5. Use our calculator. 3 times 10 to the 8 divided by 5 equals 6, and then 1, 2, 3, 4, 5, 6, 7 zeros. So 6, 1, 2, 3, 4, 5, 6, 7 zeros. Or 6 times 10 to the 7 meters. If your calculator gives you answer in standard form, leave your answer in standard form. If it gives it in zeros, count the number of zeros really carefully. For those that you were watching carefully, you'll notice I use this button down here, this x to the x times 10 to the x button. Really useful. 3 times 10 to the power of 8. It's really simple to use standard formula calculator using that one, so I recommend these types of calculators. You also need to know how to measure the speed of sound in air. So speed equals distance divided by time, which we learnt in forces. Speed equals distance divided by time. So we can measure distance using rulers, trundle wheels, tape measures, and we can use time using a timer. But the speed of sound is quite fast, so we need to use a large distance. So for example, you could stand at the other side of a football field and time how long it takes for the noise to reach there. So let's say someone stood 660 meters away, someone smashes a gong with a hammer. How long does it take for it to reach there? Let's say it took 2 seconds. 660 divided by 2 seconds gives us 330 meters per second. And that is the speed of sound that you need to remember for the forces unit. So it all links back. A simple experiment to measure the speed of water ripples. Let's say we had a bathtub and we had water waves travelling down. We'd need to measure the bathtub with a meter ruler. So let's say that bathtub is 2 meters long and it takes 3 seconds for the wave to reach the other side of the bathtub. Again, speed equals distance, 2 divided by 3. 2 divided by 3 is 0.6 recurring, so just write a lot of 6's. Meters per second, so it's much slower. The speed of a water wave in a bathtub is much, much slower. And this last bit is for physics students only, triple students only. Physics students need to know how velocity, frequency and wavelength changes for sound waves. So for example, if sound is in a solid, it is going to be fast because the particles are all touching. We can transfer the energy, we can transfer the kinetic energy, which makes the speed of sound much faster. In a liquid it's a little bit slower, and in a gas it's slow. So air, the speed of sound in air is actually slow because the particles are far apart. They require to travel a long distance before they collide, so it slows down the energy transfer. And if we look at the equation that links wave speed, frequency and wavelength, we need to know what happens to these factors if they interchange. So frequency always stays the same. So frequency stays the same. If the wave speed increases, the wavelength has also got to have increased to lead to that wave speed increase. If the wave speed has decreased, so it's gone from a solid to a gas, the frequency stays the same, so the wavelength has got to have decreased. The wavelengths get smaller as the wave speed decreases, and this becomes much more important later on when we learn about refraction.